So, hi everyone. So welcome back with the 7th lecture of supersymmetry. So let me start where we stopped yesterday. So yesterday we were trying to construct Lagrangians for n equal to theories. And to begin with, we wrote a Lagrangian for the n equal to vector multiplet, which, remember, in the language of n equal 1 supersymmetry, it is basically one n equal 1 vector multiplet and one n equal 1 chiral multiplet. Phi. They are both, of course, in the adjoint of the gauge group. We saw that there is an SU2R symmetry, which is rotating the gaugino, which sits into the n equal 1 vector multiplet, and the Weil fermion in the chiral multiplet. And because we want to preserve this SU2R symmetry, we are forced to choose a relative normalization between vector and chiral multiplet in a precise way. So we don't have freedom in writing really a Lagrangian which is n equal to 2, and it includes the n equal to vector multiplet. The only thing we can do is to write the n equal 1 kinetic term using the gaugino superfield, and the kinetic term, the gauge invariant kinetic term for the chiral. And the important thing is that here the normalization is completely locked by the requirement of having an SU2R symmetry. Yesterday we wrote this in components, and we saw that when we go to components, we can write down equation of motion for auxiliary fields, and they simply set to 0 the F terms for the auxiliary field in the chiral multiplet, whereas the D terms are non-trivial, and they are proportional to the commutator of phi with phi bar. And so the scalar potential is going to be the trace of phi bar square. So little phi is the scalar into the chiral multiplet. So the SUSY vacua, which are of course the vacua with 0 energy, they are those for which the scalar phi, it's diagonal. The vev of the scalar, it's diagonal because it has to commute with itself. So I can put it into a diagonal form. And this diagonal matrix will have to be, of course, traceless, because if we are doing SUN, as we will be concerned with. So what is the effect of this VEV? Well, the effect of such a VEV is to break the gauge group SUN to U1 to the n-1. So when we go to this phase where the gauge group it's just abelian, we are left only with a abelian vector multiplet and just matter, which is in the adjoint, but the adjoint of U1 is trivial. So we already commented that if we do abelian n equal 1 theory, there is no interaction. So this will be important later, but we expect that when we go to this phase where the gauge group it's broken to U1s, basically the dynamic is gone. So the gauge coupling, we will stop running because the interaction will be gone when I go to U1. So in this low energy phase, we will have abelian vector multiplet where we have seen no interaction. Remember, the interactions were always involving the, since every field is in the adjoint, they were involving the structure constants, and for abelian groups, this is 0. So the moduli space classically is parameterized by the VEV of these scalars, by this VEV A1 to AN, and the classical level, this is just the complex plane, so I can turn on as many of these VEV as I want, and although I have some residual symmetry, which is the VII of SUN, which is in this case of SUN, is just the symmetric group of order n-1. So this is the classical picture. Then we can wonder what happens at the quantum level. So we want to understand the effective actions for n=2 theories. And these effective actions are, as usual, are these sigma models. And we saw that because of wanting to preserve, because of n=2 supersymmetry, the sigma model that we write down as an effective action is completely fixed in terms of a single holomorphic function. Phi, which is function of the chiral field phi. And this is called the prepotential. So basically the prepotential appears in the effective action in the sense that it provides for us the generalized gauge coupling, which we obtain by taking the second derivative of the prepotential respect to phi I and phi b. So this is both phi, it's not phi bar, so this is holomorphic, and this is the generalized holomorphic gauge coupling. And then it also provides for us the Kähler potential, which we write as minus I over 32 phi bar A Fa minus F bar A phi A, where of course Fa is just the first derivative of phi F respect to phi A. So the Kähler potential, as usual, is going to provide the metric on the moduli space, because it gives us the kinetic term, the form of the kinetic term for the scalar fields. And this Kähler metric is going to be obtained by taking the second derivative of k respect to phi A, and now it's phi A B bar. And this is also expressed directly in terms of the prepotential as the imaginary part of the second derivative of the prepotential FAB. So this is the Kähler metric on the target space, which is also, in fact, a special Kähler metric because it can be written indeed in terms of this holomorphic function f. So the form of the n=2 effective action, it's then completely fixed because we will have the kinetic part for the gauge boson, which will be fixed by the generalized coupling FAB. And then we will have the kinetic part for the chiral multiplet, which will also be fixed in terms of the holomorphic prepotential. So you see that if you want to understand what happens at low energy for an n=2 theory, you basically know already the form of the effective action. So unlike what happens for n=1 theories, where interactions can pop out, new types of interactions can pop out, and so you need to, do more work to fix what is the possible form of the low energy effective action, and sometimes you cannot. In the case of n=2, you already know that your effective action will take this form. So your unique problem, which might not be extremely simple though, but it has been done indeed by Saberguiten, is to fix this function, this holomorphic function, which is the holomorphic prepotential. Besides, notice that if we take for the prepotential a half tau trace of phi square, we go back to the renormalizable Lagrangian. So what we are looking for is indeed what is the generic form of this holomorphic function when we go down at low energies and we pick quantum effects. Well, so far we only discussed vector multiplets, but we can also consider matter. The matter will sit in n=2 hypermultiplets, which in the language of n=1, it's requires introducing two chiral n=1 chiral multiplets. They're both chiral. I'm using tilde just to indicate a different n=1 chiral multiplet. So now the n=2 matter Lagrangian will be of this form. So you will have Q bar. Now you will have V with generators of the representation under which you choose gauge representation under which you choose your chirals to transform. And then now you can ask what type of interactions can you turn on, because now you have, in principle, you could add F terms, so stuff that you integrate only in d2 theta. And it turns out that if you just want to stick to renormalizable interactions, so renormalizable, remember, means that at most you can put 3 chirals because of dimension. You want to have an interaction on dimension less than 4. So at most you have a cubic coupling to have something renormalizable. And the only way to cook up something which is renormalizable, gauge invariant, and doesn't spoil the SU2R symmetry, so n=2 supersymmetry, then is to consider this interaction. However, if you drop renormalizability, so if you allow non-renormalizable interaction, you can write more terms. And but we will not discuss the low energy sigma model that involves also the contribution of hypermultiplets. So what is the picture that we have here at the moment is that, of course, also hypers can take VEVs. So the moduli space of vacua will be parameterized by the 2 sets of VEV, the VEVs taken by the scalars into the chiral multiplet that sits inside the vector multiplet, and the VEVs taken by the hypermultiplet. So it turns out that the total moduli space is actually the direct product of a moduli space MV, which we discussed a little bit, which is parameterized by VEV of phi. And this is called the Coulomb branch. And this is called the Higgs branch, which is instead parameterized by VEVs of the hypers. So these two branches, they behave quite differently because as we started seeing, this moduli space parameterized by the VEV of this scalar in the vector multiplet is subject to quantum corrections. We already saw that we can develop a non-trivial metric. So, and the metric and the generalized gauge coupling, they are related both to the prepotential. So if I can fix this prepotential, I can in the end find this metric, remember KAB, which is basically the imaginary part of the second derivative of the holomorphic prepotential. So this is going to give me the metric on this quantum deformed moduli space, and our job will be to try to understand indeed what happens to this moduli space at low energies, what are the quantum effects in this, which deform the classical picture of the moduli space where we get VEV to the scalars. And remember, when we get VEV to the scalars, the gauge group is abelianized into products of U1s. So naively, we expect that for generic choice of VEVs, we have a bunch of U1 vector multiplets. And we do expect that something can happen when the VEVs are degenerates. And then it could be that the gauge group is not completely abelianized, and there are some non-abelian gauge boson in the game. So classically here we expect singularities when VEVs are not generic, and we have non-abelian gauge bosons. So that's the expectation that we have for singularities at the classical level. We will see that at the quantum level, the picture is totally different. And this is due to the work of Cyber-Witten. Now then, there is this, instead the Higgs branch where the hypers get VEV. Here, generically, the gauge group G is totally broken. Moreover, there is something that happens, which is basically, as we will see later, lambda and tau, which lambda is the strong scale which contains the holomorphic coupling. So lambda and tau enter the effective action only in a combination of this formula, roughly. So you always have lambda appearing together with the VEV of the scalars in the vector multiplet. This is, we will see, this is due basically to selection rule dictated by the spurious U1R symmetry. So you always need to get this combination. But since here we sit on the Higgs branch where there is no VEVs for the scalars in the vector multiplet, it really means that lambda and tau will never show up in this case. So this type of reasoning implies that there are no quantum corrections. Okay, so this moduli space is going to be classically exact. And we will not discuss this in this series of lectures. And can only say also that the fact that the structure is that of a direct product is due to supersymmetry, which basically we already saw how we write down the how we write down the action. It is indeed the diagonal. So the vector multiplet part and the hypermultiplet don't talk to each other, and supersymmetry prevents that this happens at the quantum level. So you just have this two structure of a direct product. And of course, it is also possible to have mixed branches. However, it means that now the VEV of phi is non-zero, but also the VEV of qi is non-zero. Okay, so that's basically the idea. So the point is that we need to understand how quantum effects are going to change the classical picture that we have from this, which is when we turn on VEVs, we seem to go on one side, on the Higgs branch, to a theory which has no gauge group left. So, and on the Coulomb branch, instead, we have a theory which is abelian. And then we think that something's going to happen when we don't turn any VEV, and then the gauge group is unbroken. So we expect problems there. We will see that this expectation is not met at the quantum level. So before doing that, we need to have a little discussion about renormalization. So we need to discuss do this discussion in terms of wave function renormalizations. So remember when we discussed the renormalization of n equal 1 theories, we talk in terms of wave function and renormalization factors. So first of all, because of n equal to SUSY, and in particular, remember the fact that there is this SU2R symmetry that locks the normalization of the chiral multiplet and the vector multiplet that sits into the n equal 2 vector multiplet. We have that the wave function renormalization of the chiral multiplet is the same as the vector multiplet inside the n equal 2 vector multiplet. So this is going to be the same for n equal 2. Then we have written down a superpotential interaction for the interaction between the hypers and the chiral multiplet. Now, this is an F term. And remember, by n equal 1 non-renormalization theorems, this guy should not renormalized, okay? So it means that when I rescale every field by its wave function renormalization and the gauge by its ZG, then I have to have this condition that the product of ZQ, ZQ tilde, and Z phi, okay, because I rescale every field by the square root of the wave function, and G I rescale by ZG, the fact that this is not renormalized by n equal 1, it means that this has to be 1. Then also from n equal 1, remember we found that there is a relation between the gauge coupling and the wave function renormalization of the vector. This was only due in fact, to gauge to gauge invariance. So this means that this is also equal to Z phi to the minus a half. But then this implies that the product of ZQ times ZQ tilde has to be 1. But then by SU2R symmetry that remembers rotates Q and Q tilde, the scalars, into the two chiral multiplet forming the hypermultiplet, I must have that ZQ it's equal to ZQ tilde if I want to preserve this SU2R. So I get that these two wave functions are actually 1. So all in all, we have a single renormalization, which we can take to be ZG, the renormalization of the gauge coupling. Okay, if I understand how it is ZG, then I get the renormalization of everything else. Now, you remember we had this quite long discussion about the renormalization of the gauge coupling into n equal 1. So remember a little bit the lesson that we learned. So we learned that n equal 1 holomorphic coupling tau, it is one loop exact plus non-perturbative corrections. And basically the holomorphy prevents the fact that there are higher loop corrections. Remember this discussion. But the physical coupling, G physics, instead is corrected at all loops. And there is this NSVZ beta function story that instead is an all loop formula. And the resolution of the puzzle was that by the fact that there is an anomalous rescaling, that to go from the holomorphic coupling that enters into the Lagrangian, which is non-canonically normalized, to the physical coupling, basically I have to do this anomalous rescaling. And then there was this work by Arcani Ahmed and Moriyama that was really calculating the effect of this anomalous rescaling and reconciling these two effects. Now, in n equal 2, the point is that the holomorphic coupling tau is also one loop exact plus non-perturbative corrections. And if you try to go to the physical coupling by doing the rescaling, so if you do the same rescaling, so you rescale the vector you regard your n equal 2 theory in the language of n equal 1. So if you do your rescaling of the vector multiplet by n equal 2 SUSY, meaning again that you want to preserve the same normalization between the chiral and the vector, then you also need to rescale phi. So now you need to do two rescalings, and it happens, so the two Jacobians cancel out in this case. So now for n equal 2, tau is really, meaning that there is no issue between one loop x hat and NSVZ, is really one loop x hat plus non-perturbative corrections. And similarly, it will be true for the generalized coupling FAB. Although this, we will see it again tomorrow, but on Thursday, which you can rederive the fact that the generalized holomorphic coupling is exact by using spurious symmetry, spurious U1R symmetry, but that's the same thing. Okay, so now really the coupling is only fixed at one loop, and then you have non-perturbative corrections. So at this point, I think that maybe I should mention, before coming back to n equal 2 theories and low energy cyber-Witten solution, given that we are here, maybe I will just say two very quick things about n equal 4 super Ian Mills, because you will need it in the course of ADS-CFT. So remember that well, we haven't written the Lagrange for n equal 4 theories. So let's remember at the level of representations, what we did was to start from a state with helicity -1, and we start building the representation acting with the generators that now are 4. So we get acting with only one charge, we get 4 states with spin -0.5. Then we have 2 states with spins 0. Then we have 4 more states which are spin 0.5, and then another state of spin 1. So here you have 3 charges, and here 4 charges actions. So this gadget, which is the n equal 4 vector multiplet, it's composed by so 4 Weil fermions, 3 complex scalars, and 1 vector. So you can view it, so n equal 4 vector multiplet, you can view it as a 1 n equal 2 vector plus 1 n equal 2 hyper. Or you can use n equal 1 language, and then in n equal 1 language, you will write 1 n equal 1 vector and 3 n equal 1 chiral multiplets, phi A. All in the adjoint. So let's stick to this representation in terms of n equal 1 language. So the n equal 4 action will contain, again, the kinetic term for the n equal 1 vector multiplet, and the kinetic term for the 3 n equal 1 chiral multiplet. And then the only interaction that you can write down, again, preserving the symmetries, is going to be a cubic interaction involving the 3 fields, the 3 chiral fields. So in this form, the Lagrangian actually preserves SU3 times U1R. So SU3 rotates the 3 chirals. And the U1R symmetry fixes the charges of these chiral fields to be 2/3. So in fact, you can also solve for the F terms and then write on shell these Lagrangian to preserves SU4 R symmetry, which is the maximal R symmetry that you can preserve. So let me just say something about the renormalization of the n=4 theory, which we can easily discuss by this n=1 Lagrangian. So because of this SU3 global symmetry that rotates the 3 chirals, then the wave function renormalization of the 3 chirals is going to be the same if this SU3 symmetry holds. Moreover, since this theory is also, of course, n=2, then there's Z, which is the wave function of the chiral multiplet, is the same as the chiral function, as the wave function renormalization of the vector multiplet. And also there is a relation between the renormalization of the gauge coupling and of the vector multiplet. Then from W, the interaction which is an F term. We have a conditions that tell us that ZG, which multiplies Z phi 1, Z phi 2, Z phi 3 under the square root, this is just, so ZG, I write it as 1 over ZV to the half. The Z phi's are all equal and they're equal to Z phi, which is also equal to, to ZV. So you see that here I get that also ZV, it's equal to 1. But then all the other wave functions are 1. So it means that really there is no renormalization. So this theory is in fact UV finite. There are no renormalization to remove any divergence needed. The fact that this is the case, you can also see if you buy just the n=2 result that we proved before. So in n=2, we say that tau is one loop exact. So we know that tau renormalizes only at one loop. And this is true also in n=4 because tau, it's, because n=4 is at least n=2. But then if I write the coefficient, B1, that commands the one loop running of the coupling, and I use the n=2 language, so I will have 3 multiplying the inking of the adjoint of the gauge group minus the number of chiral multiplets, which are, sorry, I'm using the n=1 language, minus 3, which is the number of chiral multiplet in the representation, which is again the adjoint, because I need to put everything in the adjoint. And then you see that this is 0. So even if I use this argument, I conclude that the gauge coupling of the n=4 theory, it's not renormalized because it should run only at one loop, but the one loop coefficient is 0. And then one can argue that non-perturbative corrections are finite, so do not spoil the UV finiteness. Besides, the fact that the beta function is 0 has also the effect of making the theory scale invariant, or actually superconformal theory. And this is something I think you will probably restart from more or less here when we will discuss the ADS-CFT correspondence, which involves, of course, the n=4 super Yang-Mills theory. Okay, so this is more or less what I wanted to say about SUSY Lagrangians. So now, although really I don't have much time left for today, we can try to go back to our goal, which is the solution of the low energy dynamics of n=2 theories. So we will focus on SU2 gauge group. And this is the work of Cyber-Witten. So in this case, what we just discussed above is that we have the supersymmetric vacua, which are obtained by studying the condition of phi commuting with phi bar, meaning that the scalar phi can take vevs which are given by a diagonal matrix, which is basically, so I can take it proportional to sigma 3, and A is the vev of phi. So this this vev breaks the gauge group down to U1, and we need, there is a residual Weil symmetry that sends A into, that swaps A with minus A. So if I want to construct a coordinate which is really gauge invariant, I need to make the square of A. So I will use the trace of phi square, and I will call it U as the coordinate on the moduli space. So now you may wonder, why didn't take A square? So let's see, so phi square classically, so when I take the vev, this is going to be 1/4 A square times the identity. So trace phi square classically is A square over 2. So U, the coordinate that I'm using classically, so where I'm giving the vev, it's basically A square. But when I take into account quantum correction, clearly this is not going to be true. So this is true classically, that U is the same as A square. And I want to, and I claim that it's better to use U as a coordinate in the moduli space, because I also want to explore the region where I'm not turning on this vev. So our moduli space will be parameterized by the coordinate U, so it will be the complex plane U, at generic points where U is non-zero. We expect in this Higgs mechanism that is breaking SU2 to U1, then there would be the point U equal to 0, which is classically is the singular point where we have unbroken, well, basically we have an unbroken SU2 gauge symmetry. So there are extra massless non-abelian gauge bosons here, and we might expect that if I describe my theory in the Coulomb phase, when I undo the VII, maybe something bad happen. So what happens when, indeed, when instead U is a generic, I find myself a generic point, then we have, as usual, that the kinetic term for the scalars, they're going to generate a mass for the components of the gauge field 1 and 2, okay? Because I give a VIV in the direction 3 of SU2. So I just give a VIV in the direction of the generator sigma 3. So I generate a mass term for the other two components, and the mass is proportional to the VIV. That's the Higgs mass. And then the Yukawas will also give mass to the fermions, which are the gaugino and the Weyl fermion in the chiral multiplet for the components 1 and 2. So in the end, I find myself with one massless gauge boson in direction 3, and then also the two massless fermions, and then there is also phi 3, which I will call phi, which is the fluctuations about the VIV. So these fields, they are gonna they will sit in an n equal to abelian vector multiplet. Nice. But what happens to the fields that now they are massive? So the W bosons, so which are the vectors which are now massive, they got their mass from Higgsing. Now, the mechanism by which they take a mass cannot change the number of fields that we have. What does it mean? That if you think in terms of representations, remember that the representations of massive states contains more fields than those of massless states. But here the number of states cannot jump because this field got a mass via Higgsing. So they must sit in n equal to representations, in n equal to massive representations with the same number of fields, of states, as the massless reps. Because you cannot create fields doing Higgsing. And you know, we have seen what are the only types of massive representations that they have exactly the same number of states as mass steps. Those are the ultra short representations. But for actually for n equal 2, ultra is just short. It means, remember, that if you take the central charge and you put it in this block diagonal form, which is, so the central charge for n equal 2 is just a 2 by 2 matrix. You can block diagonalize it. And the shortness condition is only 1, so it is also ultra short, was this condition that the mass has to be always bigger than this entry of the matrix Z. So when you saturate this condition, you have short reps with the same number of states as massless reps. And this is what we need, because this is what we expect for the fields that got their mass just because of Higgsing, not because they were created massive initially. So it means that the mass of these states has to be related to the central charge, okay? And there is a calculation that was done by Olive and Witten many years ago. So they calculated the central charge. Oh, sorry, I think I'm almost, well, I ran out of time. So I will just write down something that will continue on Thursday. So the central charge can be calculated by writing, first of all, the supercharges can be in charges, of course. They can always be written in terms of the space integral of the time component of the nether current associated to the symmetry. So we didn't do this, but one can calculate the supercurrents. Okay, so these are the currents that you write using the nether theorem, using the SUSY variation. So you will have an expression, if you write your Lagrangian, you do your nether theorem, you will have an expression for these supercurrents in terms of the fields. Then if you take the time component and you integrate it, then you obtain the supercharge. Then what you can do, what Witten and Olive did was to calculate, they calculated the anticommutator of Q1 and Q2, which is supposed to give the central charge. And using the expression of the charges in terms of the currents, which is given in terms of the elementary fields, they got this expression. So it's the integral of a total derivative, which contains the components of the field strengths and the dual field strength F tilde. So A is the gauge index, which is contracted into the gauge index carried by the scalar. And then you take the zero eyes component of the field and the field strength and the dual field strength. And then they also calculated the anti-commutator of the bars. And this is going to be probably here there is a slightly different normalization than the one we have been using, but it's not terribly important. What is relevant is that this, you see this surface term that appears from this commutator can be non-zero for configuration carrying a charge, and you detect, as usual, the charge carried by a field configuration, measuring it on a large sphere. So you can, in fact, define the electric charge carried by a certain configuration of fields. So this is going to be G times NE, which is the units of electric charges. And then there is the magnetic charge, which is instead given by the surface integral, of course, of the dual field strength. These are the units of magnetic charge. So what is important is that the real part of the central charge is going to be A, which is the VII of the scalar, times the number of the units of electric charges, whereas the imaginary part of the central charge is going to be A over G, but I can combine everything into tau units of magnetic charges. So tau appears if I also introduce the theta angle. So the shift of the theta angle has the effect of shifting basically the magnetic charge. So it means that when I saturate the shortness condition, the mass which we said is going to be in this normalization equal to the square root of 2, the modulo of the central charge is going to be proportional to A, number of units of electric charge, tau, numbers of units of magnetic charge. This tau is the classical tau. So before breaking in here for today, 2 observations. So this is the very important formula. So for W bosons, we know that the magnetic charge is 0 and the electric charge it's 1. Then the mass that is predicted by this formula is just square root of 2 times A, which is exactly the Higgs mass we were expecting. So everything is consistent. But, and this will be important for the last lecture, there are also particles carrying magnetic charges. So this is not really unexpected, because if you look at the bosonic part of n equal to Lagrangian, okay, which is roughly well, you just go back and look at the bosonic part. It is what is called the Giorgi-Glashow model. Okay, it's just a model where you have you have the Yang-Mills part, and then you have some scalars with a potential, which is typically you take a quartic potential. So it's just Yang-Mills plus scalars with a quartic potential. And these models, of course, when you, for example, if you take SU2, when you go to the vacua where phi, it's equal to a square, you break SU2 to U1. And this model admits solitons, and in particular, you have the so-called Toft-Polyakov monopole solution associated to these Higgsing configurations. So I don't have time, unfortunately, to discuss these solitonic solutions. Perhaps if you look at there is a review by Alvarez, Gomez, and Hassan from '97, is introduction to S-duality and N equal to Susy-Gage theories. So it's another Cyber-Witten review. And it takes some time to review these non-supersymmetric soliton solutions, of which our N equal to theory is basically the Susy version. So in our N equal to theory, we will have solitonic particles carrying also magnetic charges, and their mass will be dictated by this formula that we wrote here. But that's the classical version of the formula, because at the moment we are working classically. But these particles carrying magnetic charges will be important, because they will play a significant role in the understanding of what happens at the quantum level on our moduli space. So I think I really extinguished my time for today. So we'll stop and you can ask your questions.